let's get started. So yeah, so first two lectures, like what we plan to do is like cover a few basics. And this is for machine learning, right? So the basics will cover linear algebra, then there will be calculus, and there will be some mathematical notations that are used pretty everywhere in the machine learning. So we'll try to make sure that everybody understands what those notations are and what those formulas are, and we will try to build up some kind of a common framework in which we can analyze different algorithms in machine learning, right? Uh, okay, let's get started. Yeah, just let me, if you have any doubts during the class, I just put it on Teams chat, right? I'm continuously monitoring it. And today and tomorrow will go pretty slow because like it is important that these basics are understood before going into any like complex concept or deeper concepts. Like, sure. So like as it's customary, like this is the syllabus. Then we will discuss this in the next class. What do we mean by supervised learning? What do we mean by unsupervised learning? What is the regression and classification? Today we'll just give you a taste of what exactly do people do in when they talk about I'm working in machine learning, like I'm using data to do and so on and so forth. Right? What exactly do they mean by that? Right? And that's what we will do today. Okay. Slide it a bit below. Yes. Yeah. So let's get on to it. This is what we'll cover today. Like I discussed, we'll first have some mathematical notations. So question is, will we going to discuss maximum likelihood? Yeah, that's too early right now. Right. We'll try. We want to build up to that. We don't want to just start with that. So we will be covering maximum likelihood estimate, but we will build up to that. We will not say that, see, this is what it is, and we'll just try to apply it. We'll try to come up with the intuition and saying that, okay, this is this is what I think we should do, and from that you will get the maximum likelihood estimate. So again, like at this point, all the things that I'm saying will sound you hand wavy, but as the things move forward, I hope you will start to understand it. So today we'll start with mathematical notations, which are common across machine learning. Then there will we'll come we will just discuss somewhat basic calculus. Again, this will be just the notations, and I hope derivatives is something that will come up again and again and again in machine learning, so that you have to understand how exactly should we use derivatives to get the best solution. It's basically minimum finding problem. Derivatives are way to get to that, right? And then system of linear equations. So you have a linear system, you have five equations in let's six variables or four variables, and then you try to solve this equation. This is something that is covered in earlier, I guess earlier lectures as well. So if you go through linear algebra, you will have this, and if you go to engineering mathematics, you will have this. Again, we don't need a too deep understanding of this right now. We will cover this on need to know basis in machine learning, and once the machine learning course is over, we can do a really deep understanding of derivatives and linear equations in the other subject that we have, which is basically optimization. So it means that we will cover the concepts which are needed for machine learning when we are going through the course. And that's what I'm right. And then we'll do a casual introduction to machine learning. And then these are the three problems that we'll discuss today. And from these three problems, we will actually start to understand what a linear regression is. That is the goal for this slide deck, right? So hopefully we'll complete this today. If not, we can always do it tomorrow. But like it's important that the concepts are clear when we move forward. So again, some mathematical notations. This might seem a bit mundane, but it's easier to get things fixed at the beginning so that it's not very. So we don't have to define them again and again. So when we have variables can are denoted by x, y, z. Basically, it is a lowercase alphabet x, y, z, or one. And set is basically capital alphabet, or it can be italic alphabet, it can be D, or it can be A, or something like that, right? It can be C as well, and so on and so forth. So, if there are n objects, again, whatever that object is. Let's say there are n images or images like whatever is like. Let's assume that there are n images which form a set in a set. We typically represent it as set D is equal to x1, x2, xn. So again, like this is a straightforward notation. There is a shortcut way of writing the same thing. It is written as something like this, right? So it is basically variable I goes from 1 to n xi. So there are n x in this set D, and then like it can be y, z, and y, right? Then functions of single variable. So we have y is equal to f of x. Again, simple mathematical notation where x is a variable, y is a variable, and f is a function. Right. So based on this, we can have functions of multiple variables. So let's say you have two variables x comma y, and there is a third variable z which is function of this. So g of x is equal to z, something like this, right? So let us have a bit more, little bit more discussion on this. So we have, let's say, I will use a different notation, and I'm just using different alphabets. So I will just say y is equal to g of x1, x2, da 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 dash. So xk maybe, right? So note that these are, again, this is the component of the set. These are some variables that I'm, so it should not be a, it can be same, it can be different, we don't care. It's just that y is a function of x1, x2 up to xk, right? That's all it is, right? So we can represent x1, x2, da, 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 dash, xk as a vector. So vector is basically, we say there is something called capital X, or it can be a X which is bolded. In if you find any machine learning books, it will be X in bolded or something like that. And I just write these numbers as a column in a matrix. So x2 x right. So y is a function of f of x1, x2, this, and I'm writing this now as a vector x. So I can just say y is equal to g of this x, this particular. Uh, any issue up to this point? So we are just discussing notation. So concept-wise, there is nothing here. We're just discussing few notations. Let me know if you find any of this confusing, or like if you want to discuss any of this. Then we have, what we have is a derivative. So derivative is basically rate of change of function, right? So we will use the standard notation. So y, again, if you consider y is equal to f of x as function, then dy by dx is basically f dash of x is basically the derivative of y with respect to x, right? Now we have a function which is we have y as a function of different variables. Then we have partial derivatives. We have partial derivatives which will be like dou y by dou x1 is equal to, again, derivative of g with respect to x1 only, right? Again, g dash of x1, while other things remain the same. x1, x2, x2, right? With respect to x1, you can write it like this, right? So there will be a different way of writing it. I'll show you how. So note that we are considering we have y is equal to g of x1, x2, x3, xk, a function of k variables. Thus, we have k partial derivatives for each x, maybe xi here. So we have a partial derivative of y with respect to x1, partial derivative of y with x2. So we'll write it like this. So first one is dy by dx1. Second one is dy by dx2, and so on and so forth. And finally is dy by dxk. So all these are the partial derivatives, right? So remember that we wrote y is equal to g of this bolded x, right? Which is basically g of, again, I'm writing x as a vector now, x2, then xk. So we can consider this to be as a vector as well. Again, this vector is of size k cross 1, and this vector will also will be of size k cross 1, right? So this is the vector of the derivatives, or instead derivatives, you can say partial derivatives, right? Where if the first dimension here is x1, this is a derivative with respect to x1. If second here variable here is x2, then this is the variable, different partial derivative with respect to x2 and all, right? So this is what we called as gradient. Again, like, this is just for notational sake. We will discuss this in a bit more detail when we actually try to solve a linear regression problem in high dimension. So if you don't, if you find this to be too complex right now, it's okay. Or if it's too confusing, we can just let go of it for now. But just for the sake of notation, it's basically called gradient of g at x. It's a derivative of multivariate function. That's all. Okay, good. Let me know if you have any issues. Now we'll get into some interesting problems. Okay, so when we are talking about machine learning, right, like there are certain ways to analyze a problem. Again, this is not a standard way, but this will help us understand different algorithms and different kinds of data problems that are there in machine learning. So this is the framework that we might follow for next few lectures. Okay, so what we will have is some kind of a data. So data can be images, a set of images. Let's use that set of images. It can be a set of images or text. It can be videos. It can be graphs. So anything that is digitally available, it can be data, right? So once we have that data, there will be a question that we want to answer. I will have one example for that. So what we want is, like, you are given some data, maybe it can be marks of students in a class, and then there will be a question that will be asked, like, what is the average marks, right? Again, that's a very naive way of putting it, but once we go forward, it will become much more clear. So we want to answer the question, like, so it can be marks also, and then our question is, what is the average score? What is the average score? And then there is model is basically kind of like a formula for average, and then you basically use this formula and this data to actually find the compute the answer here. So for next few classes, what we will see is, like, we will say that this is my data. There is a certain way the data is given. Again, we will just use vectors. I'll define that once we reach the end of today's class, and then we will put up a single question. Then we will ask, how can I solve this question using a certain formula? And then basically, how can I use computer to solve it in the optimization? So it's like, uh, any doubt in this framework? We'll see some examples of it. If you have any doubts, just put in. Okay, so consider this to be one of my problems. So consider that you are living in, let's say, Mumbai, and for last 10 years, every day you are given this kinds of information. There is a temperature, so somebody goes and measure the temperature, somebody measures the humidity, somebody measures what is the wind direction, what is the speed, Someone collects the satellite images and so on. So you have this information for last 10 years for every day of the last 10 years, right? So for the data set will be something like this. You will have all these things. Temperature, let's say it's called T, humidity is H, wind direction is, let's say, WD, then wind speed is WS, and then there is image I, or maybe use IMG, and then there is rain. So for every day in Mumbai for last 10 years, you have this tuple. So the tuple includes what was the temperature that day, what was the humidity that day, what was the wind direction that day, what was the wind speed, or maybe you can use wind velocity together. Then there is the image, which is the satellite image of Mumbai region on that particular day. And then there was whether this variable test, whether there was rain or not. Did it rain in Mumbai that day? Right. So on and so forth. So this is this tuple you have for each day for last 10 years, right? So my data set will be set of such tuples. It will be set of such tuples. So this is what I have. I have a data set D. Every point in this data set or every object in this data set is a tuple, which represents all these parameters in Mumbai or in any other city, like doesn't matter, and have this information, right? Okay, great. Then the question is, I have it for last 10 years. Now, can I predict whether there will be rain in the city or not? Uh, is the question understood? So, given this data for last 10 years, I have to predict whether there will be rain in Mumbai or in Delhi or whichever city you like today or not. So, my question is this: is this a hard problem or easy problem? Uh, So, you can write in your answer in the chat. Do you think it's a hard problem? Yeah, right. So, it is kind of hard problem, right? So again, like via regression or what kind of things we are using, that doesn't matter right now. The question is like, is it hard or easy? So it seems to be hard, right? Why is it hard? It's hard because how these variables, it's a hard problem because we don't know, don't we instead of saying don't know, we don't exactly know. We do know sometimes how these variables or maybe these values, right now. So values means like these values, temperature and affect decide the rain, right? So we don't know the exact formula that we should be using and to basically decide this. So when I say formula, then I'll say we do not have a function f to which we pass all these values, right? To which we pass all these values and the output will be rain or not rain. So we don't know that exact function, right? Such a function need not even exist, right? Because it is possible that there is another factor, maybe like if there is a belt of low pressure in the Arab Sea, that will actually cause it to rain, and that is not even here, right? So we don't even know such a function exists, and even if it exists, what exactly is that function? Is that we don't know that, right? Yeah, I'll use the color, right? So that is the problem, right? But it's not like we don't know at all. We do know sometimes. We know some correlations, but we don't know the exact formula, right? So what I do, so how can I still work with this, right? So I still want to predict whether it will rain today or not. So what I will do is basically this. Uh, we don't know the exact formula. but we do know how things are related. Again, like my weather science is, I don't even know anything about it. So what I say here does not have to be correct. It's just an example, right? So what I can say is like when temperature is low, it will rain. It rains. Again, this is my assumption. This is my assumption. So my assumption is that when temperature is low, it rains. Or other assumption can be when wind speed is so and so, it rains and so on and so forth. Right. So I can basically come up with certain rules or something like what we can say small formulas or small considerations, small we can say assumptions only, small assumptions which I believe are correct, right? Which I believe are correct and which applies to this problem, right? And I will use these rules to design. Now I am saying design because we don't know the exact function f. You can call it f star if you like, but we don't know this exact function f. So we will design a function f based on assumptions. Again, it has to be some sensible assumptions. So a domain expert can give you these assumptions, right? Like a domain expert who has been studying the weather patterns for let's say last 10 years, he somehow figured it out. Like if when certain things happen, it rains, right? So he knows it better than that. And then assumption based on those assumptions or based on those beliefs, whichever one you like, we design a function f which we will use to make the final prediction. Right? So the machine learning is all about designing this function f and then using it to make predictions. So based on what question I have with me for given data, I will come up with certain beliefs or certain assumptions which I will use to design a function f. So I'll give you one example of this design in the next when we go to the next slide. When we design a function f, and then we'll say we'll use this optimization to actually make the final prediction somehow. So a very your assumptions has to be appropriate. So for example, since I don't know anything about weather patterns, I can just make a simple assumption that if there are clouds, it will rain. So based on my understanding of the domain, I am making this assumption, right? And I can convert this into a mathematical formula. Formula can be something like this. So it will be cloud. One means it rains if and zero. So let me use a different slide. Sorry. So this is my design based on cl clouds in sky, right? So design is basically this. There is a single value that I will pass to the function, whether there are clouds in the sky or not. So the answer will one, it will rain if cloud is equal to 1, 0, not rain, otherwise. Again, it will be only taking two values, doesn't matter. Right? This is my design. So this is the design that I have based on my beliefs, right? And this is designed for a certain function. The certain function means that whether it rains or not. This is what we called as modeling, right? And it depends on what kind of data and what kind of problem that you are trying to solve. You might use different models, right? So linear regression is such a model. It's just one type of model. Then there is deep learning, like deep neural networks. They are another type of models. And then there is SVM and so on and so forth, right? The choice of these models depend upon what beliefs or assumptions that I am using when I'm using, right? And based on that, how accurate my beliefs and assumptions are, the performance of these models will change, right? So it's very hard to get 100% accurate system, but yeah, we can always hope for that. Any doubt up to this point? Now we'll get into some mathematics. Please put in if you have any doubts, right? Like today and tomorrow's certain part of tomorrow's lecture is going to be pretty. So it might think it's very simplistic, like this, all these things we know, but like just to set up some kind of a standard notation and framework for moving forward, we'll do it. Right. Okay. Let's start with the first problem, which we try to solve mathematically. So I hope everybody has seen this problem. It is like in differential equations, we generally come across something like this, right? So what we have is like we are developing a bacteria in the lab, and the bacteria grows over time, right? Because it basically splits and expands. So what we have is like at time t equal to 0 when we started the experiment, this was the population of bacteria. So maybe 10 million cells or whichever unit you like, but some population, some unit of population. After some time 5, let's say after 5 minutes, I have population 20. So now I want to check what will be the population at time t is equal to 10, right? So why would I want this? Why would I like to predict the population after a certain time? So maybe not in bacteria, in general. So answer is like resource allocation, right? So we have to produce that much grain, we have to produce so many amenities and what, right? So it's a important to take care of the people. It's an important factor, right? In case of this particular problem, we'd like to know the growth of bacteria because the bacteria can be used in some industrial setting, right? So industrial setting, and I want, so some company requires, let's say 100 units of bacteria, and I want to know how much time it will take for me to basically breed this 100 units, right? So it's something like that. Anyway, so this is the data that I have. So this is the data. This is directly from the field or from the ground. So it's in some sense it's the ground, right? This is the standard terminology. Ground truth means the data that you have collected from the real life scenarios, right? So in this case, at time t equal to 0, when we started the experiment, we started with the 10 units of bacteria. And then at time t equal to 5, we have 20 units of bacteria. And my question is like, what will be the population of bacteria at time t equal to 10? Okay. So this is my data. This is my question. Everything all right? Yeah. Okay. So now I'll make an assumption. Okay. So now let's make an assumption. So assumption is that I don't know anything about how this bacteria grow. So I go to a domain expert who is working on bacteria for last 10, 20 years. I ask him, right, how does the how does the population of a bacteria change over time, right? Again, this is just for the sake of example today. This domain experts and all, they work in a bit different manner. But let's say I ask somebody and he says that, see, the change of population at any given time t is directly proportional to the population at that time, right? So if I have, let's say, 15 units of bacteria right now, there will be a certain rate of change or rate of growth. If it's 30, it will be more than what rate you have over here. So rate when population was 15 is less than rate when population is 30, right? Whatever. So this is what he tells me, right? And this is somewhat this is some insights that he has based on he's been working in the field for so long, which is fine. Like if there are the population at this point is very large, it will likely to replicate faster, which is okay. So B, what we will do is like we'll convert this into a mathematical formula. All right. So we know that we say that let P of T denote population at time T. So like P is a function of time T, right? That is fine. Then change of population at T will be derivative, right? Is this okay? So we are directly using the interpretation of derivatives. So derivatives represent rate of change of function at a given point. And here the change of the population is basically rate of change of function P of T at time T. So we are using this. And what the domain expert has told us is that, see, the rate of change is directly proportional to the population at that time. So writing simply, we have dpt by dt is directly proportional to P of T. So this is my belief. So it was written in words before, and this is how we are writing it here. Any doubt in this? By the way, what the things we are doing right now is called modeling. I started off with some beliefs, and then now I am converting it into a mathematical formula, which I can use. All right, this is what we call as modeling. Any doubt in this formula? Okay, now we know that we just now we can just solve it for P of T. So what we want is like finding P of T based on this formula. So it's quite simple based on the differential equations. So we know that d of P of T by dt. So in initial lectures, we will try to have some mathematical solutions. And I think you should also try this out because like if the question comes, it might come from the intermediate derivative steps as well. So it is useful to try these relations on yourself, right? So dp by dt is equal to some k P of T. Again, like this. So this is some constant of proportionality. We don't know the value, right? We don't know value. We don't know the value. Well, let's think about that later, right? So we just know that dp by dt is proportional to P of T, and the k is basically a constant of proportionality that we have just introduced based on this belief that we have, right? And now we'll just solve it. So by rearranging the terms, we have k dt. Again, like you don't have to understand this integrations and whatnot because we won't be needing it. It is just for sake of example, right? And then we will integrate on the both side. What we get is ln P of T into integration of this is kt plus c. Right? Again, if you don't understand this derivation, that is fine. This is just for sake of example. And this is just to make sure that you guys try it on your own and like try to understand how this goes mathematically. Again, machine learning has some mathematical things, so you have to make sure that you are comfortable with this. So, and that's why we are solving this toy problems, right? Okay, so going forward, what we have is this ln P of T is equal to kt plus maybe I'll just use a different variable instead of c. I'm just calling it c0. It doesn't matter, right? It's just a name. Then we have P of T is equal to e raised to kt plus c0. Sorry about that. So this is my formula, and then we have P of T is equal to e raised to c0 into e raised to kt, and then finally e raised to c0 is also a constant. I just write it b into e raised to kt. This is my p of t. So remember that we started off with a belief, right? Which was just some information that a domain expert gave us. From that, we came up with the final formula. So this is how we think, we believe population P of T is related to time. This is what we think. This is our design. This need not to be true. Right? This can be wrong as well. Right? It's totally possible. This is what we believe how going to be. Now the question is now the problem here is that we don't know B, comma K. So these two numbers we don't know, right? Everybody understood this? We thought that this is our belief. We started off with that. Based on that, we came up with a formula. Now the formula has two terms, B, comma K, B and K, whose value we don't know. Please let me know if you have a doubt, any doubt up to this point. I hope it's clear. Everybody is clear on this? Great. So these variables are called parameters. Parameters of the model. So now I am saying this is my model. Again, this entire procedure is called modeling, and this is my formal formula. This is what I'm calling as my model. This is my model. And there are some unknowns in the formula, which is B comma K, and which I'm saying is the parameters of my model. So B is one parameter and K is another parameter, right? So is that clear, right? And now I don't know the value, but I do know the data. So optimization, I do know the data though. So optimization find the values of the parameters. Again, parameters in this case are B or K based on the given data. That's all optimization is. There are parameters to my model. There is some data. As this question, what should be the parameters values given this data? And optimization is basically finding B and K. That's all, right? In this case, like the data that we have is this: at time t equal to 0, population is 10; at time t equal to 5, the population is 20, and we'll just solve it using, and our model is this. The question is, how do we solve it? So in this case, it's simple. I'll just use this data and solve the value. So for example, here, right? These are the graphs at different K. Let me get darker color. So these are the curves at different values of B comma K, right? For a certain value of B comma K, this is the curve. For another value of B comma K, this is the curve, and this is the curve. We have to find the best curve. We need to find the best curve. Again, best curve based on our data. So our data is that at time t equal to 0, the population is 5, and then at time t equal to 5, the population is 10 somewhere over here, right? That is the data that we have. So for every setting of parameters B comma K, there are certain graphs that we now we will use optimization to basically solve that given data, right? So let's do that now. So remember that our model is this: P of t is equal to B into e raised to kt. So we know that P of 0 is 10, right? Therefore, P of 0 is equal to B into e raised to k0, which again 10, right? And then I guess like in the graphs we pointed out at 0 it's 10, right? That's the data that we have. Yeah, sorry about that. It's 0 here, 10. This is the point. Anyway, So it base e raised to 0 is basically 1, then it means b is equal to 10. So this is my first parameter. Right. Then I will solve for the second parameter. Second parameter is we have the second point as well. Second point at b is basically this is what we have as let me see the data again. It's 20, right? Sorry about that. So it's 20. Again, we use the same formula, but now we know the value of b, right? So this is equal to b into e raised to k5 is equal to 10 e raised to 5k is basically 20. Again, we know the 20. Therefore, e raised to 5k is equal to 2. We take the log 5k is equal to ln 2, and then k is equal to ln 2 by 5. So this is the second parameter. So in optimization, we found out b, what is the value of b, and what is the value of k. That's all the optimization is in machine learning. There are some unknown parameters of your model. There is some data. Use the data and find the parameters. That's all. And it does not matter what methods you use, right? Here we are not even using any standard machine learning optimization methods, right? Which is like you might have heard gradient descent, like the primal dual and whatnot, right? Like so on, closed form optimization. We don't even care what that is right now. We just know that it can solve. Right? Sometimes we don't even know how to solve. We just use software packages to do it, right? We should know, but like sometimes it's like that. You don't care. You just model the data. You give it to some solver, and it will give you the answers. Right. That's it. Any doubt up to this point? And now to make a prediction, use b equal to 10, k is equal to ln 2 by 5 to compute p of 10, which is what we wanted, right? Use that. That's so there is a question. Every time number of values given at it might be equal to number of every time number of values given at any point. Yeah, so that need not to be the case. So the question is that here I have two parameters b and k, and my data also have two values at time t equal to 0 and t equal to 5. Will that always be the case? The answer to that question is no. Then there are certain different ways that you have to tackle it. We'll get to that once we have that discussion. We will briefly touch upon it, but most of it will be covered in optimization, right? So, but we will do discuss the same problem, exact same problem, in linear regression as well. I'll try to motivate the same thing today itself. I'll show. So, any doubt in this first problem? Everybody understand what data was, everybody understand what model was, everybody understand what optimization is, and how are we making the final, answering the final question. I hope it's clear. Let me know if it's not. Now we'll get into linear regression. With a toy example of linear regression, we'll get to that. In some cases, can we have more than one value of the parameter based on the data? Yes, we can have different settings of the parameter. Not for this problem. This problem only has exact answers. In some cases, you might have more than one answers. I'll show you when we reach the linear regression why that is the case. Yes, so you can have multiple settings of parameters which are all correct. It is possible. So in this case though, it's unique. It's a single solution. And why is that? Because it is giving the formula is telling us that there is no scope here of having multiple solutions. Again, like the way we designed the toy problem is exactly like that. So yeah. Anyway, so we'll get a plot over here, and we'll solve it using the optimization and find out or something like this we get. And this is the plot that we finally have. Right, and we'll solve for p of 10. Let's get to the next problem. So next problem that we have is again now we are going to linear regression, right? So the next problem that we have is to predict the sale of ice cream given the temperature of the day, right? So we have this data. This is something that we observed from maybe a store or some. It is given somebody has given this data to us. So when the temperature, I'm using this notations now. The temperature is given by x, and the ice cream sale at this temperature is given by y. And there is a function f which relates x to y, right? We don't We do not know. We would like to know, but we do not know at this point. But there is some relation between temperature and the ice cream cell, right? So now I want to understand what to, again, like, yeah, this is not correct. I want to know what will be the cell at temperature x is equal to 40. So I would like to know, if this is my data, what will be the sale at x is equal to 40, so that I can have a proper stock, right? Because if I don't have enough stock and I can sell these many ice creams, I will be in loss, right? I could have sell much more product than than I'm selling it right now, because I did not know. Other issue is like, if I buy more, I will have to reserve some storage for that, and then that will again cost me, right? So I would like to buy products on a day where temperature is 40, such that I don't have to spend much more money on stocking the product, and also I don't short sell it, right? So that's the motivation here. And this is kind of like situation that we have in real life, right? But most of the people who have been in the business for many, many years, they have intuition about it, right? So they have seen that since this is temperature seems to be in this range, and I think these many items I can sell today, and they can just work all these things in their mind, right? Because they are the domain experts. But we as engineers or machine learning engineers, we have to come up with a different kind of solution, which we say is a data driven solution. We ask what the data tells us, and then we'll make some more, right? So, sure. So again, like, we go back to some expert and we can take his advice. But for now, let's assume that there is a simple relation between the sale of the ice cream and the temperature. This is something that we are assuming, and this is my belief. Again, this need not even hold. We don't even know whether this is true for the ice cream and temperature, right? Most likely it's not, but this is what I believe. I'm asking, let's make this assumption and see what happens. Maybe for certain days it might work, right? Also, so I'm saying that y is linearly related to x. So when I say linearly related, this is the function form that we generally assume. It's a linear combination, right? Again, there is no combination because there is only one x, but there can be multiple x, x1, x2, x3, then it will be linear combination of those, right? Combination of x values or x dimensions. This one more minute. This one. Okay. So is this clear? This function form? Again, why I am assuming this? Because this is very simple. Right? There is no other reason to consider this. Right? It's very simple and it's easy to start with, right? That's what we are doing. People have found out that when you have large enough data, this works reasonably well, right? But yeah, there are more sophisticated models than this, like neural networks and whatnot. We'll get to that once we cover up. Okay. Any doubt in the model? So again, like, this is not something that we are getting from a domain expert. We are just trying to learn on our own, see what happens. Sure. So now, if this is my model, I'm saying that y is related to x in this particular formula. What are parameters? What can be the parameters of the model? So we note that parameters are unknown variables, right? Unknown values in the formula. Okay, x is from data. X is the temperature. It's from data. It I can get the temperature from some other sources. Like, I can measure it myself, right? Right. So it is not unknown in the equation, right? Somebody will give me x. I have to find y. This is something I have to compute, right? What I don't know is this MNC. Is it understood? Our hunt is for MNC. X is something that I will get it from some domain data, or I can go and measure it myself using whatever instrument is available to me. Based on that, I can predict y. What I don't know in this formula are values of M and C. So M being slope and C being the offset, right? bias. So parameters are M comma C. Yeah, let me know if this is clear. I know we are going a bit slower, but it's important that you understand what is the difference between X and Y and M and C. X and Y are your variables from your data. These are variables from data. This you can measure on your own. So X you can measure on your own, or somebody can give you, and from that you can get Y. But M and C is something that is coming from your model. This is from your model, not from your data. You made some certain assumptions. Based on that, this M and C are coming up. And this is why we call it as model parameters, M comma C. Right? And now we will use optimization to find M comma C. Okay, so what can be the easiest thing that we can do here? So again, like there are all possible values of M comma C. Here you have M comma C, M comma C. Different values of M comma C will give you different lines. And we have 2 points, right? So we have, indeed with us, we have 2 points. These are the 2 points that we have. What we can do is basically use line equations, right? Slope point formula. So we have a line. Again, this is from my assumptions. Y is equal to mx plus c. And we have 2 points. This point, this point. So we want m comma c such that it works on the given data. Okay, so optimization is all about this. I know the given data. I know my models. I know my model has some parameters m comma c, and I want to find the values of m comma c which works for the given data. Is that clear? So same thing we did in case of population as well. We wanted to find k comma b which worked for the given data. We use the given data and we say that these 2 values should at least work for that, right? At least should work on that particular data. And I will, whatever works, I'll use that one for making further prediction. Right? So in this case as well, we'll do the same thing. This is my model, and I want to find the value of m comma c which works for the given data. So there is a question. What is the class timings? Yeah, it's 7:30 to 9:30. Okay. We'll see if we can move it around. But yeah, at this point it's that. Okay. Any doubt up to this point? Assumption is equal to belief. The question is that is assumption equal to, yeah, so this is not the standard terminology. This is, since we are just building up the kind of like the basic, we are using that, right? When we actually go into the exact course material, so we'll have to. Okay. Anyway, so everybody, let me know everybody understood this problem. This is what we call as optimization problem. Find m comma c and this, right? So answer to this is quite straightforward. Like we know this is a slope point formula. Right, this is m is slope and c is the bias or offset or whatever we call it. Y intercept. I guess we call it y intercept. Right. And we know the formula for this. If these two are the points, x1, y1, x2, y2, the equation of line passing through this point, we can compute it using like m is equal to y2 minus y1 divided by x2 minus x1 and so on and so on. But we won't be using this route, right? We'll try to do something which is much more straightforward, right? Okay. So let's call this point x1, y1, x2, y2, and we'll apply this formula to these 2 points. So we have y, since this line passes through this point, we know y1 is equal to mx1 plus c, which basically means that 108, again, y1 is this, 108 is equal to m, we don't know. X is basically what? 25 plus c. So equation that I get is 25m plus c is equal to 108. Then again, we have y2 is equal to mx2 plus c. And here we have 120 is equal to m into 28 plus c. And then 28m plus c is equal to 120. Okay. Is this clear? I hope this is clear, right? And now what we'll do, we have two equations in two variables. This is a linear system, right? Yeah, like subtract the two equation and all. That is correct. But in standard way, this is a linear system. We'll just solve the linear system, right? Again, the one way to solve this linear system is like subtract the equation, one equation from the other and solve for it, right? So let's quickly do that. We have 28m plus c is equal to what was that, 120? Again 120, and then 25m plus c is equal to 108 is subtracted from other. So it's basically 3m is equal to 12, then m is equal to 4. And now if you add it here, 25 into 4 plus c is equal to 108, which gives me c is equal to 8. So these are my parameters. Other way of writing it is using matrix. So we can use matrix to write this, right? Matrix way of writing it. So matrix way of writing it would be something like this. 28 this. So these are my variables now. And I will write it like this. 28 1, 25 1, MC. Again, this is something that we have already seen in Gaussian elimination, right? This is a coefficient matrix, exactly. And this is something we have already seen in Gaussian elimination. So I recommend looking into the Sachin's lectures as well on linear algebra. That will be really helpful for you. Anyway, because like these themes pop up again and again, right? So this is a linear system and we can solve it using Gaussian elimination. Or maybe we can invert this matrix and take it here and what, and so on and so forth. Right. This is understood, right? Okay, now let's make this problem a bit more interesting. I hope this was straightforward, right? It worked out quite well. We found the exact line and we can use these parameters to solve for certain. Just well and fine. Now let's make a problem bit more interesting, right? Like this is a bit harder problem than the original one. So note that we could find a line passing through these 2 points, right? Now I have a third observation. Now this is coming from the field or the ground. The ground truth tells me that when the temperature was 31, the ice cream sale was 132. Again, like this is incorrect. We want to find sale at this. And now we have third point. So everybody understood the setting, right? Instead of having 2 points, now I have 3 points. Will the solution like that before work again? So the line that we found out, before, we found that m is equal to 4 and c is equal to 8. This was the line that we have. So we have y is equal to 4x plus 8. This was the line that we have. So we know that this works for this. So because 25 and 108. So if you put 25 here, 25 is 100 and 108 is what you get. It similarly works for 28. Again, 28 is you will get 112 plus 820. Now the third point, value of x is what? 31. So the y we get from above formula. So above formula will get 4 into 31 plus 8, which will be what? Plus 8, it will give 132. Is that correct? Let me know if this is correct. Yeah. So seems like that with third point as well, the formula is working as it is. Right. Good. But did we even use the third point? No, right? But even if we would have used, we'll see what happens. So the equations we had before were this. Again, the exact solution from previous thing is working, but now we'll just try to do it mathematically, just for sake of completeness, and then we'll go from there. It was like what, 108. Then we have 28m plus c is equal to 120. And again, then we have 31m plus c is equal to 132. If I write it in a matrix form, it will be 25 1, 28 1, 31 1. So here you will have and then it will be 108, 120, 132. Now we will use Gaussian elimination. I hope everybody is comfortable with Gaussian elimination. We basically do row transformations. Again, like these things will keep on coming, like these are linear algebra things, right? And this is something I would recommend you to go through the lectures, and then so that periodically you can just refresh your memory on this, because in machine learning these things will keep on popping, right? So again, like if it's a completely new concept, we will cover it in the class, but if it's something that is available and like if everybody is comfortable with it, we'll just use that, right? So again, like now we'll try to solve this linear system. So we have this. We will find the augmented matrix 25, 28, 31, 1, 1, 1. I'm just using augmented matrix. So 108 and then it was what, 120 and then 132. Right. And this is what we have. And then we try to eliminate these rows so that it converted into something called as row echelon form. Something like this. So easiest thing that we can do is basically zero out some of the columns. Again, we'll try to zero out this and this using row transformation. So we this is row 1, row 2, row 3. So we subtract so row 2, these are the transformation that we will use. So I have row 1 and row 3 is equal to row 3 minus row 1. Again, like I'm doing it in a very short manner, but you can, I suggest you try it out. So it will be like 3 0. It will be 12. And then here it will be what, 6 0, and then it will be what, 24, right? So this is the equation that you, then you again try to zero this one out. Next transformation is basically row 3 is equal to row 3 minus 2 into row 2. So you get like this. The first row remains as it was 25 1 and 108, then 3 0 12. And then what we have here is like 6 minus 2 into 3, this will be 0. And then 24 minus 12 into 2, again it will be 0, right? So you'll get 0 over here, 0 0 0 over here, right? And then you can use this 3 to 0 out this and all, so on and so forth, that you can do. So if you see here, last row we are getting all zeros, and ultimately we are just there with 2 equations which we can easily solve. So everything works out good, right? So the final equations that we'll have is 25m plus c is equal to 108, and like then 3m is equal to 12. This we can directly solve, so should not. Yeah. So even adding a third point did not affect us that much, right? Now what we will do is like we'll change the point. Sorry. Can we say third value is redundant because after Gaussian elimination is 0? Correct. So the third row here is redundant because in Gaussian elimination we found out that the entire thing is 0. So it does not matter when we are solving for MNs. That is correct. Now we'll change the data a bit. Instead of having 132, we will have 140. So initial data was 31, 132. Now we will have 140. So why will this one? Why do we have 140 here? Can we have 140 here? First of all. So my initial data said that these 3 points of this. Now we are saying let's assume it to be 140. But can it actually happen? It can, because this is coming from ground truth. This is coming from ground. And we assume that there is a linear relationship between temperature and cell, right? But ground on the actual field, this need not to be true. There can be so many other factors that are involved, right? Maybe there was a counting mistake itself, right? So there can be a counting mistake in measuring how much cell was there when the temperature was 31. Maybe this 31 measurement itself is wrong. The temperature was something else and we measured it to be 31 because of the faulty equipment, right? Or somebody, when they were writing this data into a computer, they filed it wrong. So there are so many things that can go wrong when you are collecting the data, right? So data collection itself is noisy. There is always noise in the data, right? Unless you synthetically create it. But that is not interesting for machine learning, right? We want real life data. So there can be some issue here and there, and this is what the data we have, and this is something that we have to work with, right? So now we know that if we find a line, using these 2 points, it goes through 31, 132. But it does not go to 31, 140, right? So this point does not lie on the line, right? In some sense, 3 points are not collinear now. Right? So this is something that we will see. If you visualize this data, right, on x-axis I have temperature, on y-axis I have ice cream. So this is 1 point, this is my second point, this is my third point. So this green line is the line that we found out, y is equal to 4m plus 8, right? Note that the third point is not on this line. Similarly, I can find out line passing through these 2 points, right? But again, it will not go to this point. So which of these two answer is correct? What do you think? Is this is the correct line, or is this is the correct line? Which of these should I use to make my prediction? So see, there is no way to answer that, right? So like, yeah, we can say let's use this line, but then when we are making a prediction closer to this point, let's say somewhere here, it makes sense that we should use this line, right? Because the closer we get to here, we hope that this is what the actual scenario is like. So if, right? So for 31, if I'm making prediction as 32, I would like to use the value which is closer to 31, 32, right? Which is 31, right? But like some people might say, see, but this line seems to be more correct, right? Because it follows 2 points and so on and so forth. And so there are multiple choices that we have, right? So we'll see one of such choice. It might be an exception for there, but like, yeah, this can be an exception for that day also, right? Which of these 3 is exception? Is this is the exception? Is this is the exception? Is this is the exception? Which of these is exception? We don't know. Maybe these 2 are correct, this is wrong. Right. Yeah, again, both are correct, but which of this we should use is still not clear. So there are multiple ways to do that. So one way is to, again, like I said, we will use the closest point and we'll use that. This is what we call as k nearest neighbor, and we will not be studying that today. Other is like we will use instead of using this, we will find a trend line. So I'm not interested in the exact value, but I will use some kind of a trend, right? So which may not go through all these points, but which is close enough, something like this. Maybe that works. Again, this is a choice that we are making, right? This is a deliberate choice that we are making. So is the best fit line? Yeah, correct. So the line which fits the best is what we will use, right? It's whatever I mean by best red lines. So this is, like I said, this is only one possible choice. This is something that we are making. Okay. Like I said, the noise that happens in the data, it might be because the temperature measurement was wrong, the reading measurement was wrong. It is possible that we are assuming it to be linear, but it's not at all linear. Our model itself is not correct. That is also possible assumption or not. And there is some noise, whatever, right here and there. It's like sometimes people just do impulse buys, right? Like I'm going through some road and I see ice cream, so I like, khate hain ice cream. So it might be that also, right? It need not even depend on temperature. So on and so forth, whatever. So we will be looking at the general trend rather than the exact line. So by the way, what happens to my optimization in this case, right? In this second case, what will happen to my optimization? Let's see that quickly. So remember that our earlier two equations. Now there is a question. So coordinate geometry, we have studied a line passing through exactly halfway between 2 points. Can't we choose that one? Sure. Yeah, we can do all sorts of things. Again, that is the choice that you have to make when we are working with the data. Right. Currently, we are trying to motivate the linear regression. That's why we are going with this line, the trend line. Sure. So our ultimate goal for today's lecture is to reach a certain point where we are actually comfortable with linear regression, right? That is the entire goal for today. And to motivate to linear regression, we are making this deliberate choice, saying that instead of finding the exact line, so you can have this midpoint and whatnot, we will find the exact line, which is basically the best fit, right? So sure. So now going back, what will happen to the optimization? So we remember that we had two equations, 25m plus c is equal to 108. Then 28m plus 1 was 120. And then we had third equation, which was 31m plus c is equal to, it was 132 now, it will be 140 this time, based on the new data. I hope you are comfortable with this, right? 25m plus c is equal to 108. This was the first equation. 28m plus c is equal to 120. 31m plus c is equal to 140. So if you find this to be quite kind of like straightforward, just bear with me. We'll just expand everything we see right now into the linear regression case. We'll see this everything again, but in high dimensions, right? So again, we can solve for it. The equation that we solved similar to last time. So we'll keep this one again. So we did R2 is equal to R2 minus R1. So this is R1, R2, R3. Again, we are doing row transformations. R3. So I'm writing these concepts down so that you can have a look at the corresponding video, right? Row transformations. R3 is equal to R3 minus R1. So it will be 20 and it's basically 3, 0, 12. And then it will be 6, 0. What will be this time? 32, right? It will be 32 this time. Last time it was 24, now it's 32. Now we perform the second row transformation. The second row transformation, I'll write it over here. So I'll write it over here. Second row transformation is basically this. R3 is equal to R3 minus 2R2. First row remains the same. 25, 1, 108, 3, 0, 12. This remains as it. So it will be 0, 0. This will be now 32 minus 12 into 2. It will be what? 8, right? It will be 8. So if you see, we are getting a non-zero line here. If you convert this into equation, it will be basically 0m plus 0c. Again, it will be 0c is equal to 8, which is not correct, right? It has to be 0 here. Then only the system works. So this system is inconsistent. Again, this is the word that you will see in linear algebra. So this non-homogeneous system is inconsistent. Whatever, right? Sorry for the spelling mistakes. Is inconsistent. Again, like I'm just writing these things down so that you can go and look into the other material. At this point, we don't care about these terms, but the system cannot be solved. So we will not find any solution when we have 3 points and 1 point deviates from the trend, deviates from our assumption, right? Even if 1 point deviates from assumption, from our belief, this does not work anymore because we wanted the exact line. We wanted exact line. We said we want exact line, and that's why it's not working. Right? Then we visualize it. We see that, oh yeah, so I should not be asking for a line passing through 3 points when 3 points are not collinear. Instead, I should be asking for a trend line, a general trend line, which is something like this. Again, there are other choices also, like the nearest neighbor or the midpoint thing that you discussed. Or instead, I can also say, let's not use a line, maybe use a parabola. Even that is possible. But this is not a linear model, then this is a quadratic model. We don't care at this point. Right? But that is also possible. So the fault can be in different things. In real life, it can be the data problem, it can be the model problem, or it can be some outliers as well, right? So it can be anything in between. So this is an error. This is the error that we are making, and it can be coming from any of these things, and we still have to work with it. So instead of saying that I want the exact line, I will say the trend line. So there is a question. Can we choose any scalar which is not equal to 0 line lambda? Can we choose any scalar which got equal to 0, which is not equal to 0, line lambda, and we can form vector matrix from there? Yeah, you have to elaborate. I don't understand. Okay. So now, yeah. So now let's go to the trend line that we so-called trend line, right? So what we want is like, we want to find some line which correctly captures the general trend, right? So we want to find m comma c. These are the parameters which correctly captures the general trend. So we are now relaxing the requirement that line must pass through the 3 points, like 25 108, then it's 28 120, and then 31 140. We are not relaxing, but it should be close enough. But the line should be close enough. Again, we will define what do we mean by close enough, right? Or we can also say approximately passes. Approximately passes. Right. So we'll define what that is, right? Let us say, let's assume yeah. So let's assume we have some m. I'll just write m is equal to m0. Again, it is just some value, right? It may not be the correct value. And c is equal to c0, right? Let's assume that. Now when we say it approximately passes or close enough, what do we mean by that? We say that the line uh, y is equal to m0x plus c approximately passes through the 3 points. The 3 points are, again, I will write x1, y1 now, x1, y1, x2, y2, x3, y3. I'm just using the variable names. So their exact values are, like we know, it's 25,108, it's 28, 120, and then 31, 140. The approximate mass is 3 when y1 hat, again, like I'm using a different notation now. Hat means predictions, right? Y1 hat is equal to m0x1 plus c is close to y1. So what we did is basically this. We took the value over here, which is 25. We put it in this equation for some m0, c0. And whatever we get, we say that this y1 should be close enough to y. And then the line is good. So we compare these two. So this is what we called as prediction for a given line. Again, it's just a fancy way of saying it. We are just applying we are assuming that the values are this, and we are applying this formula, and we are getting some value, and we are finding how close is this value to the ground truth value. This is ground truth. I hope this is clear. Then similarly, we can have y2 hat is equal to m0 x2 plus c0. Again, is close to y. And similarly for y3. So y3 hat is equal to m0 x3 plus c0 and then y3. Is this okay? So we'll compare the predictions for a given model m0 c0 with the y, right? Yeah, so now exactly this closeness is basically we are computing the error now, correct? So again, like when we say close enough, we will have to compare this with this. So there are different ways to compare, right? So we compare. Now I am using yi hat and yi for I equal to 1, 2, 3. So we compare. So there are different ways to compare. One way to compare is basically take the difference yi minus yi hat. This is one way, one possible choice for comparison. The problem is that this can be negative or positive. Right. Second is we can take a mod like this. And again, this is good. This is always positive. This is positive. But derivatives don't like it. Again, we do use it, but we'll get to that. How exactly do we use it? We don't have the concepts which are required to handle this. Derivatives don't like it. The third one. So second one. Can you please explain? Okay, so let me write the third point and then I'll explain the second and third. So then there is yi minus yi hat square, which is positive and good for derivative. Okay, so note that this is coming. We can use any of these things. So first of all, this is not a good choice. This is not a good choice. I'll tell you why. So let's assume that you have 2 points, right? The error for point 1. So let's call this Li. We can say Li equal to this, Li equal to this, or Li. But this, in first case, let's use this point. Li L1 turns out to be 5. Let's assume that, right? In one case. In for second point L2, it turns out to be minus 5, right? That is possible, right? For some value of m, you can always find what, right? So for first point, this term L1 is 5. For second term, it's minus 5. So overall error, when we actually add these two, will be 0. So L1 plus L2, and let's assume L3 is basically 0. Again, some weird line is there. Again, this will be 0, right? So overall error that we are getting in this case is 0, even though two of the points are not fitting well. It's very, it's kind of like not a good fit, right? 5 minus 5 is a very high error, right? So is this understood why this is not a good choice? Any doubt in the first case? No, right? Yes. Now in the second case, the error will be L1 will be 5, L2 will also be 5. Okay. And we can compute L3 is again 0. So then total is L1 plus L2 plus L3. We will get 10. Plus L2 plus L3, we will get 10. Right. And we can solve it. And we can say this is fine. And we can say this is a good measure of error. Sure. But we need to find, and this is we are doing it for some M0 C0, right? Some M0 C0 is which we already know. We are using it for that. But we want to find the M comma C which has the least error. Our ultimate goal of the optimization is to find the values of the parameter based on the given data, right? The best possible parameter based on the given data. Now I am saying this is my error, or this is my goodness of it. I want the error to be as low as possible, right? I want the error to be as low as possible, but for that, I will need to use some optimization techniques. Again, like if you don't get it, in the next slide, you will, when we actually solve the problem for this, you will understand what I mean. Okay. Anyway, anyways, so we have to use some kind of an optimization here. We have to find this minima, which requires computing derivatives. Again, if it's not clear right when we actually try to solve it, you will understand. While third one does not have that issue, right? When we actually solve for it, we'll see why that's the case. Okay, let's get into it. So everybody understood what do we mean by error though? Error or closeness of fit. Everybody understood that? At least the concept everybody understood. So what we want is like we want to find some line which is close enough, and when we see close enough, we will see that we'll compute some error, and that error has to be low as much as possible, right? Okay. Now I'll write it down, and now we'll get into the optimization, and then you will understand the derivative stuff as well, right? So let for a given line following formula. Again, this is based on our own understanding from the last slide. Formula represents closeness of fit, or basically error, right? Whatever, right? Sure. So formula is basically this: L is equal to L1, error in the first point, plus L2, error in the second point, and L3, error in the third point, right? Which is nothing but y1 minus, again, for a given line with parameters m comma c. So these are the parameters, right? We saw it for m0 c0, but it can be any m comma c, right? So we can just write this m1 minus c whole square plus, again I am using the third one. We'll see why. Then y2 minus mx2 minus c whole square plus y3 minus mx3 minus c whole square, right? I can write it like this. I goes from 1 to 3. Y minus mxi minus 3 whole square. Right. Note that. What are the parameters of my model? It's m comma c, right? These are the parameters, right? Right. Y and xi are from data. So these are from model. These are from data. I cannot change the data, right? I cannot change the data. Once you have the data, it's always going to stay with you. What I can change is the parameter of models, m comma c, right? So this error is a function of parameters of the model, m comma c. Let me know if this is clear. This error I am computing this error or the closeness of it for a given line with parameters m comma c, y is equal to mx plus c. Okay, I have a given data with 3 points. I computed this error as this by MSC. And since this data is always fixed, only thing I am allowed to change is parameter c. So this entire thing is a function of m comma c, right? Now, optimization is basically this. Find m star c star for which the error is the lowest. And that will be the best fit that I have. So this is some fit. I want the best fit. The best fit line will have the lowest possible error, right? Everybody understood this? So this is the error for some line m comma c, but I want to find the line for which the error is the least. That is the best fit line, right? Everybody understood this? Any doubt in this? Yeah. So mathematically, we write it like this: m star c star. So this is the line, parameters of the line, the best fitting line. These are the parameter of the best fitting line. Is basically that line for which the error is the lowest, right? So my error is basically this, and we want the lowest, the minimum error, right? So for all, again, I'll write it down. I'll write down the exact meaning of this, and this is the notation that you will see in time and time away. This means find the values among all possible m comma c pairs or values. Instead of this, I'll write this. Find the point among all possible points for which L is the lowest. So in calculus, we say this is the minima. This is the minima of this function F. So this is L is a function of two variables, and this is the minimum of that function. If we are talking about in calculus, right? So m star c star is the minimum of this function, L of m comma c, where m is the slope and c is the y-intercept. Right? This is the parameters of our model. So optimization is about finding the best parameters such that this error is the least, or it is the lowest error. Any doubt in this notation? No doubt, right? Is this clear? Okay. So there is a question. MC should be chosen from our assumption to minimize the error. Correct. So this is based on our assumption. The question is that m comma c pair should be chosen from our assumption to minimize the error. Yeah. So we started off with the exact line. We found out that we can't even find such a line. So then we say let's assume instead of that, let's say we choose to find the line which is the best fit, and we say that the best fit is defined as this. So everything here we are making it on our own, right? We are making these assumptions that the best fit should be like this. Again, whether this is correct or not, we'll get to see that later, right? For now, let's assume that this is the right way, right? Again, we made these choices based on certain things. Now we'll explain why we did not choose this, but we chose this. Now we can explain. Anyway, so everybody understood this, right? Minima part, everybody understood. So this is entire thing is based on our assumption only. So okay. Now, how do we find minima in calculus? We find minima using derivatives, which are equal to 0, right? Correct. Now the problem is, note that absolute function or mod function does not have a derivative at x is equal to 0. Again, like you can go and check the calculus books for this. So if this is your mod function looks like, again, this is 0. This is how your mod function looks like. It does not have a derivative at this point. So we can, if the answer lies there, we don't know. So we cannot use this derivative method directly on this. So it's not very derivative friendly, right? Finding a minima of mod function is difficult because it's not differentiable at certain values. So the method that we are going to use, which is basically dy by dx is equal to 0, does not work for mod as it is, right? There are certain additional things we have to do, which makes the problem a bit harder, right? We don't want this. And that's why we did not choose this. Because we don't want to solve hard problem. We first want to solve easy problem. We'll again get to this in some time, 2-3 lectures, we again come back to this when we have enough knowledge. But at this point, we know this cannot be solved using derivatives, but we know this can be. This is not good. We know that this just gives 0, even if there is huge error. This is okay, but this is hard to solve. This is both okay. This is okay, easy to solve, and gives positive all the time. So let's use this one. That's it. And that's why we made that choice. Again, it does not mean this is wrong. It just means that it is harder to solve, so we don't want it. We make choices which makes our life easier, right? Why would we deliberately make our own life hard? Right? That doesn't make sense. Okay. So now we have this. The function is like this. M comma C. I will again write the function. I goes from 1 to 3. Sorry. Y minus mxi minus c whole square. Right. Everybody understood that? Now we will use derivative solve. Right. So we'll take derivative with respect to m. I should have written it here only. Summation of 1 through 3 y minus mxi minus c whole square. Let me know this is clear. You are looking at m comma c as variables because those are the parameters of your model. Y and xi is from data that you can't change. That is given to you. You can't change that. Okay. So now we will compute dl by dm. We will set it to 0. And then we will compute dl by dc and we'll set it to 0. So this is a multivariate function, 2-variable function. We compute the derivative with respect to each variable and we'll set it to 0. And we'll see what happens, right? So what we get is basically this. Dou L by dou M. Again, this is M comma C. I'm just not using the notation. Use this. I goes from 1 to 3. Then you have 2 into y minus mxi minus c into what? We are taking derivative with respect to m. So it will be minus xi. So this is using chain rule. This is chain rule. Again, this is the standard way of computing derivatives, right? So again, I hope this is clear. We are taking derivative with respect to m. Always remember that. We are not taking derivative with respect to x. we are taking it with respect to m. Yeah. And then we will equate it to 0, right? So what, again, this 2 gets cancelled out, and what we get is basically this. Summation I goes from 1 to 3 xi yi. So we take this again, this negative minus 2 because of 0 it goes out. Xi yi is equal to summation I goes from 1 to 3 xi square into m plus summation I goes from 1 to 3 xi into c. Okay, so I take this xi, multiply it with yi. This is the value I get, and this is the equation that I get. So it is a linear equation in m and c. So these are the coefficients. Is this understood? These are the coefficients. This, and this are the coefficients of the equation. M and C are unknown. Right? Everybody understood this? Now let us do it for, again, dou L by dou C. We are computing. So we computed partial derivative with respect to m. We got one equation. So this is equation 1. Equation 1. Now we are taking derivative with respect to C. We should get equation 2. So it will be again summation I goes from 1 to 3. I'm directly writing the derivative now. yi minus mxi minus c into derivative, since we are taking it with respect to c, it will be minus 1. We put it to 0. So the second equation that we get is something like this. Summation I goes from 1 to 3 xi m plus, again, it will be like what? 3. Right? It will be 3. Yeah, I guess it's 3c is equal to summation I goes from 1 to 3, and then y is this. Just check. Let us just check this is correct, right? So this is the derivative. So we will, this 2 and minus 1 will in multiplication. So they will, and since this is 0, they will cut out. So summation yi, yes, summation yi, summation xi, summation xi, and summation from 1 to 3c is 3c. Is this equation correct? Like, everybody understood this equation? This is the equation number 2. And then there was equation number 1. Equation number, I'll just write it down here again. The summation I goes from 1 to 3, it will be xi square, right? Yes. It was xi square m plus, again, summation I goes from 1 to 3 xi c is equal to summation I goes from 1 to 3 yi xi. Great. So these are two equations in two variables. So two equations in two variables. So Gauss is happy. Gaussian elimination. Again. So life is so simple, right? Two equations, two variable, everybody is happy. Let's solve this, and right. So again, in matrix form, it will be something like this. I goes from 1 to 3 xi square. Summation I goes from 1 to 3 xi. Then summation I goes from 1 to 3 xi, and then 3. And here MC in the matrix. I'm just writing it in a matrix form. I goes from 1 to 3 xi yi. And here, I guess it's just y, right? I goes from 1 to 3 y. Okay, so this is a linear system. We know x1, x2, x3, x1, y1, x2, y2, x3, y3. We know the values of this, so we can compute all these three terms, right? Is this correct? We can compute all these three terms based on the values that we have. just 25,108, then 28,120, and then 31,140. We just compute this value and we solve this linear system. We'll get M and C values, right? Which are all this, right? Since we are equating derivatives to zero, this should be minimum, right? Again, this can be maximum as well, can be minimum or maximum. Minima or maxima. But it turns out that this is, in this case, it's minima. In this case, it's minima. We'll see why that is the case in next lecture. For now, because like a derivative of zero means either it's a minimum or maximum. You have to compute the second derivative. So you have to compute dou 2L by dou M square. And we have to show that this is greater than zero, and then yeah, then it's maximum. So again, like I'm not going into that right now because after some lectures that will automatically come in. We have to address that there, not now. For now, let's assume that's okay. And we solve the system. And this is what we called as linear regression. So the entire thing that we did, our assumption that it's linear, our assumption that we want best fit line, our assumption that the loss, again, I did not say loss, the error is the quadratic function, quadratic is the square function. And coming up with this solution is basically linear regression in one variable. So again, like we can do and solve this in the class, but for sake of time, let us just plot this. So I solved this problem. Again, you can use computers or you can solve it by hand. And then we basically find value of M and C and we plot that line. So this is how it turns out. So by the way, we have not clearly defined what a regression is. We'll do that in the next class. So this is just to provide you with the notations and the techniques that we are going to use. So everybody understand what is derivative, everybody understand what is a linear system, everybody understand what is argmin is, everybody understand what optimization is. The today's class was only for that side, right? Right. So this is, now I'm saying this is linear regression in one variable. I'll discuss that why that is the case in the next class, and we'll define what regression means exactly in the next class. Anyway, so this is the line that we get. So see, it's not passing through any point, but it is somewhat like a general trend, right? That is what we wanted, again, because we thought that that's going to be a good thing, and we'll use this line to predict the cell at temperature 40, which is basically at this point. Right. Okay, so now there are some questions, right? So we are coming up with a system of two equations, which is basically this. Does a system of two equations always has a solution? Not that it's not a homogeneous system, it's a non-homogeneous system. So it did not always have a solution, right? When if these two lines are parallel lines never intersect, so there will not be a solution. So will that ever happen in our case or not? Will this happen? Does this happen for our problem? So our problem of this, like this problem, does this ever happen in our problem? We have to see. It may or may not, right? We have to see whether that happens. Okay. But yeah, we'll discuss that in the next one. And then yeah, we'll start with the linear regression. Any doubt in today's class? We'll stop now. So like content is done. Any doubts? Again, today's class, it may seem that we are going too slow, and like it's basically engineering mathematics. I'm not feeling the machine learning yet. Just bear with me for 1 or 2 classes. It's better to get these notations and this basic concepts clear before we go into machine learning. So that's why we took it in a very different route, like fitting a line and all that. Like it's a bit quite it's a quite different from the direct machine learning syllabus that you have. It's like starts off with the linear regression, but yeah. Yeah, so if you feel this was a bit heavy, yeah, we can discuss this again in next class, because like it is easier to spend time on this, get things right on basics, than spend time on explaining the harder concepts. So if you find this is too mathematical, you have to bear with it, because like in machine learning you will spend time on mathematics, right? But we will try to make sure that we explain the math in an easier way as possible, right? We So now the question is, how much probability do we need to study for ML? So if you are asking about probability, okay, so before that, if you find anything confusing in today's lecture, right? Let's do this. You come up with few points. In the next class, I will start with those. We'll cover that and then we'll go to linear regression. Right. Make sure you absolutely understand the mathematics here. If you don't, we'll do it again. But that is paramount, right? Like we have to do it. You have to get it right. Then only it will be easier for you to understand the remaining of the machine. So I suggest just if you don't understand, just let me know. We'll discuss this again. Right. So now let's go into studying that. So probability will not be probability. You should know random variable and Gaussian function. Some of this we'll cover in the class. So this Gaussian function, for example, we'll be needing after 2 lectures, most likely. This we will cover in class. So, but it would be easier for you to understand if you know what random variables are. Right? Again, since this concept we'll be using, we'll touch on this during the class, right? Second, in linear algebra, just look into system of linear equation. So, how to solve system of linear equation? The Gaussian elimination, basically. Again, if you don't know, let me know in the next one. We'll do one example for this, right? But yeah, so I guess Sachin has covered this in his lectures anyway. So have a go through that. Probability this part. Then, sir, for you 15 days, what prerequisite math we need? Prerequisite maths is like again how to compute derivatives. Okay, yeah. So this is all you need. So this is basically maxima minima. Whatever is required, we'll cover that in class anyway. But if, I think it is okay. If, it would be better if you know the derivatives beforehand. And now, like just one thing, you might feel this is too mathematical, but yeah, machine learning is mathematical. So at least for at the gate level, I think they would be a pretty math intensive on this. So this is kind of like the basic that we have started with. Any doubt you have in today's class, let me know tomorrow. I'll cover it for you. Right. So for example, why does a derivative at zero means a minima? If you have a doubt in that, let's discuss that. We need to make sure that this you are comfortable with this notations, you are comfortable with this kind of like concepts. And if there is an issue, feel free to ask. So again, since we are beginning the course right now, it is okay to go extremely slow here. Because once we get the basics ready, linear regression is going to be just an extension of this. Once you understand the case in two dimension, extending it to higher dimension is quite easy. So just let me. I hope this is okay. Oh, okay then. I guess we can stop. Hmm. To us, can't the derivative be maxima? Yes, like I said, the derivative can be for maxima, and yeah, we just assume it to be minima for now because we don't want to go into second order derivatives. That will be a bit more complicated. For now, just let's just assume it's a minima. There is another way of doing it. So y is equal to x square is a parabola, right? So the graph of that function looks generally like this. So it cannot be maximum because you can always find an x. Always find. Okay, so let's get to the equations that we have. That will be easier to understand. Yeah. So why it cannot be a maxima, right? A maxima is the highest value of the function, right? So there can no other value that this function can take which will be greater than the maximum, right? But I can always set here, we can always set m to be a large number, and c also to be a large number, and we can increase the value of this function to whatever we want, right? I can just take m to be like 100 million, right? And c to be like 200, 400 million. And I can always have a number greater than that. So I can always set value of m and c such that this function is higher. The value of this function can increase arbitrarily. I can increase this value of function to any point I want by setting m and c to very, very high values, right? So there is no maxima here at all in this function. But we're still getting derivative to be zero. So since there is no maximum, it has to be minimum in this case, right? So there is a mathematical way of proving it by saying the second derivative, take second derivative and show that it is not zero or it's greater than zero. Yeah, but that will bring in unnecessary complexity at this point. Easier way to show that is like, see, I can always get a value, higher value by setting m to be higher and c to be higher, right? Like since it's square, it will give very high value. It does not even have a maximum. So, and since there is still some m comma c for which derivative is zero, it has to be minima. It can be a saddle point, but again, unnecessary complexity at this point. So can the last matrix be always be solved? Yeah, that we will discuss in the next class. Can we always solve this matrix or not? That is something that we have to discuss in the next one. Okay, let's stop now. Goodbye.